Okay, so welcome to the session. My name is Dale Sparling. Today we're going to talk about how NXP's USB-equipped ARM microcontrollers can simplify your designs and speed up the development of your products. To get things started, we'll go through a brief review of USB, its architecture, and some of the commonly used terms. After that, I'll explain our chip driver and bootloader feature, which is what the session's all about. And finally, we'll run through a demo that shows the HID and mass storage driver and bootloader in ROM. Okay, what is USB? USB stands for Universal Serial Bus. It was originally designed to connect simple low-speed peripherals to the PC and replace the serial and parallel ports. The standard includes the hardware components like the cables and the connectors, and communication protocol that transfers over that hardware. The cable itself holds 4 wires that include 2 for power and ground and a twisted pair that carry data using differential signaling. The advantages of USB are that it is low cost and everywhere. USB has many variants, and there's a picture of all the connectors up there. The first widely used version of USB was 1.1, which was released in 1998. It supported 1.5 megabit and 12 megabit data rates. 2.0 was standardized in 2001 and added a high speed rate, which supports 480 megabit, I've heard. On the go is a 2.0 supplement that allows 2 devices to talk to each other by making one of them act like a host. USB networks use a tiered star topology made up of a single host and up to 128 devices. The host can talk directly to the device or to a hub, which can connect to other devices or other hubs. And you can have there's up to 7 tiers in the network. In a USB network, the host talks to devices by connecting pipes to the device's endpoints. An endpoint is a communications channel on a device with a dedicated physical buffer associated with it. Well, 2 of them actually. A device can have up to 16 of these endpoints, and each one has both an in and an out buffer. That's for going to and from the host. Every device must have at least one endpoint called a control endpoint. A pipe is a logical connection that the host creates and connects to these endpoints on the device. A descriptor is a data structure produced by the device that tells the host what kind of device it is. I'm a mouse, I'm a keyboard, I'm a printer, something like that. And the enumeration process is what happens when the device is plugged into the bus. So you plug in a mouse, the host detects the presence of the mouse, it creates a pipe to the devices, to that mouse's control endpoint, and directs it to return a descriptor. That descriptor includes the device's class. There are 4 different types of endpoints. A control endpoint is used for short, simple commands to the device and status responses back to the host. This endpoint is used to send the descriptor back to the host during the enumeration process. All devices must support a control endpoint. Interrupt endpoints are used by devices that require a quick response, like mice and keyboards. Isochronous endpoints provide a guaranteed data rate, but not guaranteed data delivery. They're used for streaming video, like webcams, and they can drop frames. Bulk endpoints provide guaranteed data delivery, but not guaranteed data rate. Mass storage devices like flash drives would use this type of endpoint. They'll do like retries if they drop data. USB descriptors report their attributes using descriptors, or devices. So when a USB device is plugged into a bus, one of the first things that happens is it sends a descriptor up to the host that tells it what type of device it is, and there are several different kinds of descriptors. Some of the things that these descriptors include, they include like the vendor and the product ID, the manufacturer name, the version number, USB version number supported, the class of the device, the maximum packet size, things like that. The host uses this information to determine how to interface to the device. So it determines what kind of pipes to set up and communicate with it. The operating system uses this information to decide what driver to load. So this is the whole process. So step one, the device is detected on the bus when it gets plugged into the connector. The host assigns an address to that device. It creates a bidirectional pipe connected to the device's endpoint 0, that's the control endpoint, and sends it a command to return to a descriptor. And then step two, the device creates the descriptor that tells the host all about it. It sends a descriptor back to the host as a status return over that control pipe. And then the host reads the descriptor and creates a new pipe connected to the device's interrupt endpoint, because this is a mouse, so it uses interrupts. The operating system loads a standard Microsoft mouse class driver, and off you go. So these are our ARM USB product families. I'll be showing the one on the top in green, the LPC 1343 part, on an LPC Espresso board. It has a Core M3 ARM core and a USB device, 32K of flash, and 8K of RAM. So these are the key features of the USB on the 1343. So it's fully compliant USB 2.0 full speed device, 12 megabit per second. It has 5 logical endpoints, 1 control, 1 isochronous, and 3 that can be configured as interrupt or bulk. It supports soft connect, which lets you connect and disconnect in software. It's kind of like disconnecting the cable, but you can do it in software without physically disconnecting the cable. And it has its USB drivers and a bootloader in ROM. Here's a block diagram. Again, you'll notice, the key thing to notice here is the size of RAM and flash. It's not very much. So everything you need to do needs to get crammed into that small space. So some of the challenges that you have when you want to deal with USB, you're faced with, is you have to, first of all, you have to write the firmware that talks to the USB device. USB is a pretty complicated machine, so this takes a significant amount of work. You have to then debug that firmware, and you have to tune the performance of the firmware. You have to update it in the field once you have it going, which means you got to write bootloaders and you know, custom programs that people aren't really familiar with. And then there's resource management. You know, you only have so much memory on this part, so you have to figure out how best to use it. So all these things take time and money. So these are the things that this chip addresses. So it implements the USB device functions in ROM, and this frees up 6K extra K of memory, so that you can put that into your product. Binary ROM driver circumvents potential tool vendor porting issues, of course. And it's tested and it's certified and it works properly. So these are the on-chip driver features. It's just it's a standard SoC, ARM-based SoC, but with the USB, with all the driver functions in ROM. So this is the interface to those drivers that are in ROM. It's very, very simple. All your program has to do is call a couple of functions, one to initialize and one to connect to the USB block. And again, these are entry points in the ROM that you call. And you supply your own get and set report functions, which the ROM code turns around and calls back again to do its functions. On the HID, it's get and set report. On the mass storage device, it's memory read and memory write. And that's it. It's very, very simple. So you can develop your product quite quickly without having to worry about writing lots of complex device code for the USB. Okay, so the LPC 1343 has an on-chip USB bootloader. This bootloader implements a mass storage device, and it can eliminate the product manufacturing step. Basically, whenever it boots up, it shows up as a drive, and it presents to you a binary file that contains the contents of the flash, and you can delete and overwrite that file, and you've programmed the part. So you don't have to have any kind of a special flash burning utility. You just use the operating system's file system to do it. And I'll show you that in a little bit. So we have a security code read protection feature that prevents copying of the flash contents in 3 different ways. So CRP1, you can allow partial programming, so you can just program certain parts of the flash. CRP2, you can allow partial programming only if the whole chip is erased. So this is good for during your development process if you want to update part of the flash, but don't allow somebody else to update another part. And CRP3, it completely disables the bootloader forever. And once you do this, it's permanently unflashable. So this is what you would do once you got your program working properly on the manufacturing line. You'd set this mode. That way you know that nobody else could ever change the program again. It's a secure feature. Okay, so the demo. I'm going to show you today writing a human interface device driver using the on-chip driver, and also I'm going to show you flashing, programming the part using the USB bootloader. So the hardware I'm going to be doing the demo on is called the LPC Espresso. That small board at the top is the development board. We sell it for $30. This part of the board to the left of the mouse cursor is JTAG, and you can actually cut the board right down here and then remove that once you're done. And this part right here is the breadboard, and there's the chip right there. So you can actually make a product out of this board if you want, but this what you do is you buy this board and you do your development on this, and then Okay, Embedded Artists is a company that makes the baseboard, and this thing plugs right into this socket. And this board has, extends out all the different peripheral connectors. So it's a full development product, and I think you can get this for $150. Huh?
That's great.
That's right. For $150, you can get the whole thing, I believe.
The Espresso platform by itself, the board itself is $29.95 off the shelf, and the IDE comes for free. So you get a 128K download limit on the IDE, which basically makes it free monitoring for free.
Yeah. So you can start developing very quickly and very cheaply. So you can go to our website, right here, listed right here, and download the tool and install it. And you start it up and you select the HID ROM project and you build and run it. So I actually have it up and running right now. This is what it looks like. This is an Eclipse-based product, so it's if you're familiar with Eclipse, then you'll be familiar with this. Whenever it first comes up and installs, it gives you all these projects to work on. And today we're going to work on this one right here. So to start up and run it, you select the project, and you select build, and it builds the code. and you select debug and it runs. Okay, so it's running right now. And we supply a little demo program, a little HID demo program that talks to it, so you know that it's working. Now, just like any debugger, when it comes up, it's going to break on the main or close to that, so you can set breakpoints or do whatever you want. I'm just going to go ahead and run the demo. Okay, it's just started now. What that program did was it called the init USB. It called connect USB. It set up a data structure with its callback functions, and it started running. And here it is. Now this, if I can get the manufacturer string, the product string, serial number, and if I check this checkbox, you'll see. Let me bring there's the camera board. And I can turn the red LED on and off. That's this one right here. These are the main four things that you do. You write the callbacks and the IRQ handler. You set up the driver structure. This is a structure you hand to the initialization code. It tells it what type of class it is and where the callback functions are. You initialize the chip, and then you initialize and connect to the USB driver. And all of this code is located in this file here, USB HID ROM. So the first thing you do is you write your in-report callback function, and then you write the out report callback function. The demo code's right there, so it's easy to do. And you write an IRQ handler. Notice that this right here is a pointer into the ROM that contains all those functions. And then there's a structure there, and then the offset is, in this case, is the interrupt service handler. All right, this is where you're setting up the device structure. So you're telling it's a USB. You're telling it what the USB vendor ID, product ID, device type, the string descriptor, and a few other things about it. And then you, okay. The string descriptor is in this file right here, this USB descript.c, and that's how you have to set it up. This is Unicode, so you have to set it up with a 0 after every character. And then back here, this is where you actually point to the get and the set report callbacks. And this is the code where you set up initialize the chip itself. And again, here's that pointer into ROM, and now you're calling the init clock pins function. All this is in the ROM, so you don't have to write any of it. You just simply call it. It's all debugged, ready to go, nice and fast. Here's where you're initializing it. This is where you're handing that structure that we just looked at a minute ago. That structure contains, tells the USB, the driver a little bit about your device. Oh, where's my mouse? And then you connect. And that was it. As soon as the connect function was run, the HID started working. So that's probably about the fastest USB code you'll ever write. Okay, another part of this, another feature is the bootloader. It's also in USB. And what it does is when it comes up, it'll present itself as a drive in Windows. and it'll show you it'll give you a file that contains the contents of the flash that's on the chip, and you have the ability to delete that binary and override it with another binary of your choice. So what I'll do is I'm going to take that binary, the HID program that we just ran in the debugger, and I'm going to convert it to a binary file, and I'm going to override it into the flash device, and then I'm going to boot the board up without the debugger, and it'll just come up as that same HID device. But to do that, you have to you have to produce a binary file, and there's a few utilities that come with a tool that do this for you, right? So determine the size, copy the object, binary format, add a checksum. This is important. You got to add a checksum to the file. So in order to do that, I'm showing you part of the project settings in this tool. There's a post-build steps, and the default string that's there whenever you start up this tool looks like this. So you need to change it to this string in order to produce the binary file. So when you go and get your product, just again bring up this slide and just copy and paste this string right into that field on this slide right here, and then you're good to go. NXP's LPC 134X, I think there's a 3 and a 4 chip. They both ship with drivers and on-chip ROM. The drivers implement USB device functions, so you don't have to. USB bootloader is also on the chip, so you can burn the flash using the standard file system. This saves 6K. Remember, there's not very much flash and ROM on this part. It's a very small part, so every byte counts. And this eliminates 6K of that memory you have to tie up. The binary ROM driver circumvents potential tool vendor porting issues. And the code is tested and validated and debugged